Hello community! It is a beautiful Sunday morning and today is going to be wild. Today will be chaotic and it will be complicated and it will be simple and it will be beautiful. So let's start here. We have a brand new research paper about the optimal communication protocol of multi-agent AI systems. And you remember in my last video when we looked here at 7 agents that had a configuration of a chain, we said, hey, a linear chain might not be the optimal communication configuration for 7 agents and a single knowledge graph if we have a dense communication and interaction pattern. And now we have a new research study. And this study says, hey, we have AI. So let's have an AI system that will decide for us the optimal configuration of multi-agent system. So how we do this, how we approach this. Now the main idea is simple, to represent our complete AI agent as a node. And we will construct here custom topologies based on the task complexity. And since we as human, we don't want to use our own brain to find here the perfect configuration of 7 agents and how they communicate, when they communicate, about what channels they communicate to each other at what time intervals, we will use here an AI system and we will use here an old auto-encoder. And it will be, yes, a variational auto-encoder. And since our object is not an image but a graph, it will be even easier to understand what is going on. Talking about easy, hello, if you're new to AI, look, it is easy. We have here nodes, node 1 to node n, and each node is here an AI agent with a particular task. Now the task complexity will define here the optimal configuration. And our task, or the task of the AI, is to find this optimal configuration. Now in my last video, where I said I am agent, I showed you that with new OpenAI notation, we can say here node 1, it's an agent. So what we have, 4 lines of code, the class of an agent of a base model. We have a name, we have GPT-4 Omni, Mini for example, as our LLM, our vision language model. Then we have the instruction, your helpful agent for a specific task, and normally you would do it in the way ABC. And then we have the tool, all the external communication. You can interlink to your supercomputer center at CERN if you are a theoretical physicist, or you connect to some biomedical databases. All there, the world is here for you. So you see, this is a simple configuration. But now, if we depend on the task complexity, so if I give you a very simple query, the AI system with multi-AI agents will have a very simple configuration. Do not waste energy. Do not waste time with predefined complex configuration that are designed for a much higher complexity, but go with the appropriate complexity configuration for the query. As I told you, we have external API tools, web search, then we have code compilers if you want to work here in Python environments whatsoever. And if you look at this, you understand, if you have seen my other videos, that this is simply a configuration as multi-agent as graphs. And you remember from this video where we talked about automatic agent workflow of LLMs, A-flow, this new methodology, we talked about that whenever we can see edges here in a representation of structure that is a graph, for example here, GPT Swarm, language agent as optimizable graph structure. This, I told you, is here a beautiful way to see this. And GPT as Swarm parameterizes and optimizes here the fully connected graph distribution. So we have a solution, but we have other solution. For example, if we go here, if we see the edges now as a representation of a structure like a neural network, that can represent complex nonlinear relationship between the nodes, allowing here for an adaptive and learnable workflow based on input and feedback. I showed you in this video that we have here the beautiful dynamic LLM agent network that October 2023, Stanford University and Tsinghua University, Georgia Tech, they give us a beautiful solution to this. So our chat LLMs and our dynamic LLM agent networks utilize simply a multi-layer perceptron-like layered graph. However, and this is now the reason why we have a new research paper, all these attempts, whether predefined static topologies or those iteratively optimized topologies, they remain input independent. So they are not specific to the complexity of the user query. So consequently, they fail to be task-aware and adaptively design their own topology, their communication protocols, and their configuration that really suit here the complexity of a specific task. So this is here our goal, this is here what we want to achieve. We want to build now a new system that is really input dependent on its complexity level. So here we have. So first step, we just have to build an LLM-based multi-agent communication protocol. Beautiful. But we have 3 topics that we want to be integrated in the protocol logistics. We want to have an effective communication. So the communication structure must effectively produce the qualified solution for a very specific task with a very specific domain knowledge and a very specific complexity. Second, complexity. We want to have a complexity adaptiveness. Plus, it should be robust if we have adversarial attacks. So we have to establish a communication protocol, a structure here between our agents that even if somebody would try here to cut 1 or 2 of our communication pipelines, the system will still be reliable and a robust system. So easy. A, B, C. Great. So to design now this communication topology that inherently is now respecting all those 3 principles, the authors of the study proposed here a new multi-agent communication graph designer. Why should we as humans think about this? Hey, we use an AI to build here the optimal system, and they call it here a G designer, a graph designer. However, I would call it here a multi-agent communication graph designer. So I will talk about a MACP designer. But at first, let's have an interrupt. That's a good idea. If you're new to AI, from a green grasshoppers, think about this. Is complexity LLM, the model, specific? I did a simple experiment. I said, hey, Llama 3.2, a 1 billion instruct model, not any way that I quantized it. I said, no, the pure 1B model. And I said, hey, give me here an example of a complexity query that you as an AI think is a level 3 out of 10. And then give me one with a complexity level maximum 10 out of 10. And if we want to answer, is a complexity LLM specific? You see this here, I'm a 5-letter word. If you take away my first letter, I still sound the same. If you take away my last letter, I still sound the same. But if you take away my middle letter, I do not sound the same. What am I? For a Llama 3.2 1B, this is a complexity 3 out of 10. What is the 10 out of 10 example? There are 3 switches, but they are not labeled. Each switch corresponds to one of 3 light bulbs in the room. Each light bulb is either on or off, and you can turn the switches on or off as many times as you want. But you can only enter the room 1 time to observe the light bulbs. Can you figure out which switch corresponds to which light bulb? This is the complexity, and do it with your own LLM that you like. Your home LLM, your specific LLM that you use, get it. Just ask it, hey, what is a simple complexity task for you? And what is the most complex task that you as an LLM can imagine? So you get a feeling and you can answer then, is complexity LLM model specific? Because I did now here a simple chat GPT for Omni, and I said the same, a level 3 out of 10. And Omni tells me, and this is a screenshot here, calculate the escape velocity from Earth. When can I escape here the gravitational field of Earth? I just do some calculation and I see this is a 3 out of 10. What is a 10 out of 10 for Omni? Solving a general relativistic problem, the gravitational time dilation in a Schwarzschild geometry, like for example in a simplified black hole, and it gives me a simpler reasoning process here on the mathematical equation to solve here time dilation because of gravitational fields. So you see, this is here a 10 out of 10. Now you compare this and you ask yourself, is complexity LLM specific? You can do this not just on text, not just on physics, but do it on code. I ask here complexity level 8 out of 10, now specifically here in the coding area, and for Omni comes back and says, hey, to fine-tune here a BERT model for a sentiment classification using custom data. And it gives me here the complete Python code here for fine-tuning here a BERT model. So you see, it really is specific to the domain, your coding, your text, your logical, your causal argumentation. Is complexity LLM specific? What do you think? So let's come back here to our very simple visualization. And now imagine that all your networks, all your multi-agents that we have now, they only have a Llama 3.2 1 billion free trainable parameter model instruction tuned. Do you think that this, although we have 1, 2, 3, 4 identical Llama 3.1 1B, do you think this system can now solve a complexity task by me as a user as equal as a 4 Omni system? And I'm not talking about quantized systems here, just a normal 1B system. So you answer now the question, is complexity LLM dependent? And if we find out that maybe there is a dependency, you also understand that how the communication protocol is important, how they communicate, because this node here has access to the web search, this node here has access to a code compiler, this node, I don't know, has some access to some specific SQL or whatever. So you understand, for a specific task, for a specific complexity, we do not want a general solution that should work for everything, for everybody, but we want to have an optimized solution. And we try to keep here the LLM maybe as small and as unintelligent as possible, because then we can put them maybe on an edge device, on a phone, or on an iPad, or on a whatever. So there is a simple optimization problem. Beautiful. So here, will a communication protocol discover now for Strawberry on a complexity level 8 out of 10 work now if we have multi-agent constructed only of a Llama 3.2 1B model? What is your answer? What do you think? Okay, this was the end of the interrupt, and now we are back here. So if you're not anymore new to AI, you're gonna enjoy this now, because this is not the original study. And they talk about, hey, if we have now a multi-agent system with multiple LLM instances, and maybe different LLMs and really fine-tuned special LLMs for specific domain-specific tasks, let's start here. We model now this multi-agent system as a directed graph G, and we have vertices and we have edges. Now, all our vertices represent, as I told you, a set of nodes. And the edges, you're not going to believe it, denote the set of the edges. Each node corresponds to an agent, an AI agent with an LLM and with access to the internet or whatever. It has an interaction with the environment. And nodes can now be formalized, and we have now 4 different kinds of dependencies. We have the base. This is the language model. This is what I was talking for the last minute. So it depends here on the quality of the complexity solvable solutions of your LLM. Then the role. This is the agent's pre-assigned role or function. You remember in the system prompt when you say, hey, you are now, I don't know, able to create French lyric, or you are now theoretical physicist. You have a role defined. Important is the state for each node. This represents the agent accumulated knowledge and a complete interaction history for this particular agent. And plugins, you know it, all the external tools, all the function calling, all everything that is available, web search, code compiler, file read, SQL, whatever you have. And then it is easy. No? Then we start to play with this system. And we say each LLM-based agent. Yeah, Please note that here there's really excellent and they specify LLM-based agent because you can have rule-based agents also. So they are also intelligent in a certain way because if we humans sit down and we define the most important rules for our agents to follow, we do not need to have the intelligence under quotation mark, of a large language model. A simple rule-based model might be enough for you. It depends on the complexity of your job. But here we go with LLM-based agents. They receive now a prompt and they generate a response. And this is more or less all that we need, no? Because now we have here our system prompt represents the system prompt encompassing its rule and the state. And we have the user prompt, and this simply denotes the user prompt, which includes here the given task, the responded from other agents, the instruction from other agents, the communication protocols from other agents, and all the externally retrieved knowledge from our function calling. It is a rather simple topological structure. And now again, is complexity LLM specific? Because remember, we have here one brain in the loop and only one brain, and it is an LLM. Then, of course, if we have now the node and the edges, we need to have an adjacency matrix. This just indicates here the connectivity of our complete graph. And this, I think from mathematics. Now, let's focus here on the communication pipeline. I have here on the left side, if you're interested in the real publication, and on the right side, I have here for my green grasshoppers. And with the help of Strawberry, I tried to find here an easy to understand summarization. So let's start here with the communication pipeline, and then let's have a look at this. And you choose what you want to read first. Given now a query, Q, the multi-agent system engages now in a round of iterative utterances. Collaboratively drive the agent toward producing here the final solution A based on the cumulative dialogue exchanges. It is a big game. You start now here to iteratively run through all possible combinations for a specific query, for a specific multi-agent system, for a round of, 100 iterations, 1000 iterations. So you see, this system takes time. These systems need to experience multiple hundred, maybe 1000 iterations depending on the complexity of your task. And at the beginning here of a dialogue round, we have a mapping function. This is applied to determine here the execution index for each agent. And yes, maybe the neighborhood is a little bit too complex. But in the end, you get, if you want, here an answer. And OR represents here the output of a very specific agent, which could be a rational, an answer, a partial solution, depending here on a specific context. And the output is generated based on the system prompt and the context prompts, consisting of the query and all the messages from the other agents. For my green grasshoppers, iteratively refine a multi-agent correlation through multiple dialogue rounds, gradually converging on a final solution based here on the cumulative playable interaction among all the agents. Now we come to the interesting part. Now the authors tell us, hey, we now have a formal definition of the protocol of our multi-agent system. And you might say, hey, this looks interesting. Yes, but it is simple. Look, we just have 3 terms. 1, 2, and 3. And we have additive terms. It couldn't be simpler. So, let's follow the idea before we have a look here at the formal mathematical notation. They say, given here an LLM-based multi-agent system, with our little, Llama 3.2, we establish the following objective as an optimization principle or a protocol. So it is simply an optimization task like almost every time in AI. So, what we have now in our terms. G represents the feasibility parameter space of our graph G. Beta are simply some hyperparameters we can tune and adjust to our solution. We know the utility evaluator function. This just gives us, hey, this is a good solution or this is a bad solution here. This is here our U. Then here the norm of G of our graph measures now the computational and the communication overhead of the entire graph. This means, can I have a more simple graph structure and come up with a good solution, or do I need to increase here the complexity of my graph to arrive at a good solution? So this second term here, the norm, gives us here the communication overhead. And then here our third term is simple. I told you we have a third argument if we have adversarial attacks, and this should be a robust system. So Q hat and G hat simply denote query description multi-agent after the adversarial perturbation. And you see, this is it. So we have a performance term, then we have a complexity task adaptiveness term to find here the minimal best graph solution for a particular query, and then we just want to have that the whole system is robust if somebody tries to cut us off one communication pipeline of our graph. And this is the whole optimization principle. So you see, immediately you could say, hey, I could add another term. If you have something in your system that is important for you, add a term. Maybe you see, I have dependencies between multiple parameters, add an inference term, add a perturbation term. So you can immediately optimize this, but we go now here with the original paper. And at the end of each dialog round, a certain aggregation function is adopted to generate the answer. So if we have after each turn, after each iteration, we got here an output, we got a response, somehow we have now to aggregate here the final solution. You have a lot of possibilities. You can go with a majority voting. You say, I think R17 is the best solution. Or you can aggregate all the agents' response and you see, okay, what is the sum of all the answers? Or you have simply the output of the last agent. You say it's always the last one, or whatever. You can have a formula that runs over all this. So the aggregate function is specific to your task, specific what you expect from the system as an outcome. And after you have k rounds, 100 rounds, 1000 rounds of this, you have your final answer. You see, it is a simple optimization problem. Now that we have the protocol of our multi-agent, multi-AI agent, multi-LLM-based agents, now it is time that we say, hey, great. And now we build a second part. And the second part is we want to have MACP, a designer, a multi-agent communication graph designer that will build us here the perfect configuration of our, let's say, 7 agents for a particular task. And this is here the official publication by the authors of this study, and I love it. It is so beautiful because it gives you here immediately the overview of what's going to happen. Note, we have 4 compartments, and we're going to have a look at this. Now, the start, we already know. We have a query, beautiful, with a certain complexity, great. Then we have our agents, those are now nodes. And for each specific agent, as I told you, we have now a dependency on the base LLM, on the role that this particular agent is going to play, on the state and all the communication that already happened, if you want a kind of a memory, and a plugin, the access to external, I don't know, supercomputer or just a Python environment, whatever. And the roles. You can say, hey, agent number 12, you will behave like a teacher. Agent number 7, you behave like an economist or whatever. And you have all the Python compiler, image question answer, all the tools that are available for you in the network. Easy. Construct is now much nicer. As I told you, we go now with a graph structure. So if we build all these nodes here, let's do this. So we have now a node encoder. We have to encode here the nodes. And I will show you, we have a task-specific node, and then we have the agent representation in the network. And then If we have here a special defined task, I will show you, this is here where more or less all of the memory is also allocated here. And then we just look here at all the possible permutations here of the communication protocols that can happen here in our predefined multi-agent system. And yeah, we have a multi-agent network, that's all there is. But we will have now an anchor structure and a little bit more, and I will show you this how we can do this and why we need it. Yeah, let's have a look what's gonna happen afterwards. No problem, we're gonna go step by step. I just want to show you this now in a complete way. Then we design here this machine that will do the optimal configuration of our multi-agent topology. And here we will use an autoencoder. We will use here a graph autoencoder. Where we use here a variational graph autoencoder, and I will explain what the encoder is doing and what the decoder is doing for our communication graph. And then, not the fourth step. Now we have to go here in medias res. So let's have a look. So how we start? We construct now our multi-agent network as an input now to this beautiful AI machine that will output us the perfect configuration of our 7 AI agents with the perfect communication pattern for a particular task. So this machine is called our G designer or MACP designer. Now, how does this system work? How can we program this as an AI system? Well, we define what is the input. So we have our graph G, but now it's a little bit different because now our X agent is now the node agent. Every node is an agent. The node agent feature matrix. This is now our X agent. And A represents the connectivity matrix. I already have shown you this. So for the feature matrix X agent, we employ now a node encoder. Why? To transform each agent's unique profile that is now specified in text into a new mathematical representation, and we want this representation to be a vector. So what we do, we transform this into a fixed length embedding representation with a node encoder. So we have now the complete textual description of the agent's LLM backbone, all its assigned plugins. We know what it can do, we know how it should behave, we have the system prompt of all of the agents. And now the node encoder can be realized using here simple text embedding from sentence birds or other systems. So you see, we transfer now, as we've done years ago, our textual information in a vector representation with a node encoder. And you might say, Jesus, if we only would have a channel here on YouTube that has more than 50 specific videos on how to do from BERT here, bidirectional encoder stack for a sentence here on how to do this here, the complete coding for the pre-training, for the fine-tuning, how to create the data set, how to explain here this transformation from a textual understanding to a vector understanding. Yes, if we would only have those channels. And then we have to have an anchor topology. So, as I told you now, the next step is that you ought to tell us here we introduce now an additional task-specific virtual global node. Node is a vertex, so V for vertex, and this is now summarizing the task if you want. Now, there's a speciality because now this node is here bidirectionally connected to all the agent nodes, enabling here a global storage sync. So here we have all the information available specific to the task, facilitating now a smoother information flow among the agents. And now, since we already have a vector representation of the nodes, now the task node is also encoded here by our node encoder, by our SBERT system, also that it is now living here in the same mathematical space as our other nodes, as our other agents. We have now to start somehow, so we have to have a start configuration of the system. And the authors say we provide a simple anchor topology, A, which serve as a starting point for our intelligent machine, our G designer, our MACP designer topology design process. Say, for instance, give me a code generation task with 3 agents, the manager, the programmer, and the code reviewer. the anchor topology at the very first step, at the very beginning, the start configuration, could be configured as the simplest chain structure manager programmer reviewer, reflecting here the typical easiest to think workflow of the code completion. For my green grasshoppers here formulated in other words, in simpler words. And then comes now the beauty. Because now we have transferred here the complete functionality and the complete complexity of our configuration of our multi-AI agent system into a new mathematical space. And if we have this now, we can use the tools that we know for years. So if you're completely new to AI, you might be now a little bit overwhelmed, but in practice, we just use the tools that are 1 year old or maybe 2 year old, but we know exactly how to use those tools. So now we bring in a new tool set to solve the problem that we have. And the problem that we have is simply design the communication topology for a multi-AI agent system, but do it in a way that the system learns how to do it for a specific task with specific agent, with specific API call functionalities. So it is just a learning process that we want to start now. And the tool that we use for that learning process is simply here a Variational Graph Auto-Encoder framework. Now, if you are not familiar with a Variational Auto-Encoder framework, this might be now a little bit of a rough ride in the next 2 minutes. So therefore, I would say, if you like my kind of explaining, I have here quite some videos you see 1 year ago, 2 years ago, where we use those models, variational autoencoders, for image generation. And now we use it for a graph generation. We use it now that the system does not learn how to generate images from text to images, but now we want that the system learns graph configuration of multi-AI agents. So we use this tool. Yeah, you don't have to look here at a vector quantized variational autoencoder. No, just the normal variational autoencoder, but instead of images, we go now with graph structure. And here I show you how you can code this. We have a Kullback-Leibler divergence. We can come back to this in Python and in Colab notebook. If you want to have a deep dive and understand what's going on here, I think these are 3 videos that might help you to understand this. You just look here in the search functionality of my YouTube channel. You put in whatever you want, and hopefully you get all the videos that you need. Plus, I was never ever talking here about specifically here a graph variational autoencoder. I was only talking about an image variational autoencoder. So you have to read this paper. So this plus this will bring you up to speed. What is the current state of the art? Causality-inspired spatial temporal explanation for a dynamic graph neural networks. And they go here exactly here for a dynamic variational graph-based autoencoder framework. This will help you to understand what is coming up now. Read the study, it's a beautiful one, but I also found here, remember this was here in a conference, they had a presentation. And I found the slide of the presentation, and there are 4 slides that here, this is the address if you want to download it yourself. Here you have the mathematical formula, but maybe this is more interesting here. How you disentangle here the trivial and the causal. You have a causal mask and a dynamic mask. Then you have here the formula for the contrastive loss function. This is the formula here for the dynamic loss function. And then the 4th step is simply the spatial temporal explanation of the prediction loss and the sparsity loss, how it's combined. So maybe a little bit of deep dive, half an hour you have to invest now in this paper, but then you're up to speed. Great. So now we use this tool. So our new intelligent machine that should learn graph, our MACP designer, uses this tool. So it deploys now a variational graph-based autoencoder to generate a multi-agent interaction topology, which is formulated here. Beautiful. But the main idea is, always focus on the main idea before you're impressed by mathematical formulas. We have an object, we send it in a tool, the tool starts to encode this like an image, then has it a temporal state, and then the chance is Now from the encoded state, we want to decode it back to the original image. And we do this so that the AI system learns how to do it, how to interpret all the elements that it has encountered in the training data set so that it understands how to build images from a text to image generator. We use now the same idea. We have, just focus on the simple idea. We have an encoder and we have a decoder. Let's have a look at this, and for my little green grasshoppers here, we have an encoder. The encoder learns here a latent representation for each node, for each agent, by encoding the anchor topology and the features of the agent, and then the decoder simply tries to reconstruct the original pattern. Reconstruct a sparse task adaptive communication graph by optimizing the agent interaction while ensuring the robustness and minimizing the communication overhead. Remember, from our protocol we had 3 terms. So this is now a huge optimization topic that we have with a very specific tool, an autoencoder, a variational graph autoencoder. This is the basic idea. And now if you have seen my videos and read this paper that I showed you, you immediately understand all the formulas that you see here. And you see it is always back to this idea of an encoder, decoder, and the learning process that's happening here in the pre-training until the AI system is able to do a text-to-image generation. Here in the original text, you have now the decoder described. First construct a parameterized sketch graph S, which is then refined in a final multi-agent communication topology. Yes, beautiful. But again, this is our simple decoder that is just trying to come back here to the original solution. Now, if you are not sure about this, I showed you here. I just asked here a normal ChatGPT for Omni. Hey, describe here a graph convolutional network. So a real easy one. And since this is around now for, I don't know, 3, 4, 5 years, this is, every AI system should know this, you know? So if you're really stuck somewhere, just ask your AI system, hey, explain here a graph convolutional network layer. Then you say, explain a latent embedding. How is it done? Explain this. Let's go to the latent space sampling, to the posterior distribution. I explained this in my video, but this is here just by an AI system. Maybe this helps you. Then we talk about here the Kullback-Leibler divergent terms, why you need it. The summary, therefore, of the complete encoder, what it does. Maybe you like this representation better. And then we just have the decoder. The role of the decoder is predict the existence of edges between the nodes. Based here on the latent embedding of the 2 nodes, probability of an edge existing between the 2 nodes is determined by applying a similarity function. You say, hey, I know this to the latent embeddings. We're always coming back to the same ideas we have in AI, but just sometimes a little bit of mathematics. This is the code that you code here, by the way, is a little bit more advanced, but the ideas are always more or less the same, no? Edge sampling, task-specific refinement, reconstruct the original graph from the latent embeddings. That's all there is. And how we achieve the embeddings with an expert system. You see? Easy. So now I hope you understood here the design phase of a graph autoencoder, and then we are more or less left just with an optimization cycle. So how we do now the optimization of this intelligent AI machine, this MACP designer? Okay, so let's have a look at this. As I told you, we need time because the system needs to learn all of this. Yeah? So we have K round of interaction, and hopefully all these agents converge to a final solution given my specific query as a user. What we want, the communication topology Comm is now refined iteratively using the posterior probabilities, ensuring that the final structure balances here. You remember my 3 points: efficiency, task accuracy, and end-to-end. Network, the result is a sparse communication network that optimizes here for both the performance and the robustness. And as I told you here, we want to have a topological complexity that is adequate to the causal complexity of the query. Great. This is here now the complete algorithmic workflow presented here by the research team for the G-Designer optimization. Complete. So they say those are all the steps that we have to run through. But remember, this is only a little bit more complicated because we use the tool as a variational graph autoencoder. If you use another tool, it can be simpler. You could even come back and say, hey, as a human, I want to look at this. I want to use my own brain, and maybe I, as a human, I found here some critical rule-based decision modules that I want to hard code into the system. So if you are working here on one domain only, and you have only more or less one specific task, you don't need the AI machine to come up with 10,000 solutions for 500 domains. If you are absolutely focused on one task only in your one domain, you can use your brain and maybe hard code here an optimized structure that you have known to be successful, that brings you the result that you want to see in this worst case scenario that you do not want to use an AI. You can use your human brain. So don't be impressed by any mathematical formulas. You can do this also by hand. Great. Yeah, for my green grasshoppers here. System starts by establishing a multi-agent network based on the agent roles, states, and available tools, along with a task-specific query node. Then, as I told you, it uses a variational graph autoencoder to encode the node features into the latent space and decode the final communication graph. In each iteration, the agents collaborate by exchanging information through the constructed graph, the communication pipelines that we have in the graph, the edges, and the system aggregates their responses, whatever your aggregate function will be. And after each communication round, the system's parameter updated via gradient-based optimization that we know here to improve the overall performance of the communication topology. You need time, you let it run a long time, and you got hopefully the best performance of the system in a specific configuration. By the way, this is the study I was talking about the last 5 minutes already. GDesigner, architecting here a multi-agent communication topology via a graph neural network. Shanghai AI Laboratories, Tongji University, whatever this is, Amara University, beautiful. Have a look at this. This is really fun to read, but you have to know a little bit the tools of the past of AI. So you have to have experienced the last 1 or 2 years of AI, and then this should be no problem at all for you. And the authors now talk to us and say, hey, we have 2 new innovations, no? We have at first here the LLM-based multi-agent communication protocol. Remember our 3 terms, the 3 additive terms that we can improve on. And then we say, hey, and then we have here an optimization. We have here an effective, adaptive, LLM-powered multi-agent communication graph designer, termed MACP designer, that will build the perfect communication configuration of multiple AI agents with multiple tool use, with multiple knowledge graph, blah, 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 for you. If you just give it time, you let it run, and you will get here the perfect topology. What is nice, that's why it's in blue. Multi-agent topology must be designed based on the task complexity. Remember, we did this only to have, now the additional step is we have an input sensitivity based on the complexity of the user task to ensure here a minimal communication overhead. This is for all the global corporations that say, hey, we have millions of requests to our strawberry system, but you know what? The requests, the human queries are so simple, I don't need strawberry to answer this. I can go with a mini system. So it is cheaper for global corporation to apply here a cheaper infrastructure, an AI infrastructure, if people just want to play around with a system and their complexity queries are not at all there, that you need here the heavyweight fader, the huge LLMs for maximum performance, and the introduction of sparse and task-aware communication topology, this was here part 2, not only enhances the performance, but also provides some robustness against adversarial attacks. I will talk about this. If you have kind of a communication redundancy in your system, it will be so helpful because, yeah, this will be a text of another video. Just to tell you, yeah, it's also robust, and robust will become important in future AI systems. As you can see, this optimization principle for our simple protocol, our multi-agent communication protocol, is nice, but it is task specific, it is LLM specific, and domain specific, knowledge specific. So what you should consider, and that's now why it's in red here, this framework reliance here on the graph neural network and the autoencoders might be computational really expensive because the system needs to learn. And the more domains you want the system to be able to handle, let's say I want only just the physics domain to be handled, but if you say, hey, I need biology, I need biochemistry, I need, I don't know, medicine, and I need physics, and I need mathematics, then this thing, this automated best configurational exercise can become quite computational expensive, and this means monetary expensive. You can help yourself here if you go with a highly task-specific idea, meaning it needs to be fine-tuned for all your specific different problem types in your environments only. You are not Google. You don't have to provide a system that is valuable and works for 1 billion people. You and your company have a single and one cause problems. So reduce the complexity to the max and optimize only on your specific task. It is faster, cheaper, and has a better performance. Or you go my way. I'm currently doing this as I record this video. I built here also kind of a self-learning system on top, because what we have, if you just choose another perspective of this, we have now a vast search space available for us to find here the optimal configuration of our multi-agents in a new mathematical space. And here we can also apply here a self-learning system, but it has to be a system that is really exploring here the complete search space, because maybe in some corners of the search space, some solutions are hiding. So this is an interesting problem in itself, maybe another video. And if you don't want to have this complexity of a self-learning system, you can help yourself. And this is the last tip. When you start the fine-tuning, look at the initial conditions. Look at the start configuration. Because the more clever you use here a specific start configuration for the system, the faster your system will converge, and the faster we will have here a proven solution that works. So invest some thoughts into the initial condition that you give the system to start from, and the better your start conditions are, hey, you will see the working complexity solution for a specific task are great, utilizing here your multi-agent configuration and your new communication protocol. Beautiful. This was a Sunday morning 2 cups of coffee video. I hope you had a little bit of fun. We went a little bit more in the complex domain of AI, because some of you sent me an email and said, hey, AI is so simple. Is there a little bit more challenging AI? Is there something that makes our little brain goes, yeah, that sounds interesting? I hope this was also a video for you, but I also hope that if you're new to AI, giving you an idea how those systems work, how you can use them, how you can play around with them. We have a huge toolbox that are just modules to build here a modular approach. And this is here, you're really here at the leading and bleeding edge of AI research. And it would be great to see you in my next video.